Hello everyone and welcome to my YouTube channel. This is part 2 of the competition from 30 days of ML. So I have decided to divide the videos into parts instead of days now. And there will be several parts for the competition. Today we are going to take a look into feature engineering. Before we dive into that, I will show you something at the leaderboard. So what's going on is a lot of people have similar scores and someone has posted some kernel which has scored really good, and most of the people are submitting that kernel, so don't get disappointed by that. Focus on your own model, focus on feature engineering, focus on cross validation, and try to select the submission which is best for you. You must remember that the leaderboard is only 25% of test data and final result will be on the other 75%. So if you just copy paste blindly, submit someone else's code blindly without taking a look at the code, without knowing what's happening, you might end up in thousands of ranks. So currently there are 3,000 teams, and today we are going to look into feature engineering. Okay, so before we start with feature engineering, let's see the code from last time. So if I go here, and this is competition day 1 baseline, where we created a baseline with 5 folds. I made another kernel, another notebook with 10 folds, so you can use 5 folds or 10 folds depending on what gives you the better results. So here I'm going to take everything from here and I will copy paste here. And instead of importing ordinal encoder, I'm going to import from sklearn import pre-processing. So from sklearn import pre-processing, and this is just like last time, and I will copy this part, I will keep it here. One more thing that I will do today is I will use GPU instead of CPU because it's much faster for XGBoost. And let's copy all these things and we have it here. So we have everything in one cell now, everything in one cell. And today we won't be generating the submission file, but we will be calculating the predictions instead. So here I will create a new list, call it scores, which is an empty list. And this empty list will be filled up by the root mean squared error for each fold. So here my RMSE is mean squared error, y valid, prints valid, and squared false. Here I can print fold and RMSE, and I can append scores.append RMSE. Okay, and here I can print np.mean. So let's see if we import an np. Yeah, we did. I will calculate the mean of scores, and standard deviation of scores. Okay, so we have XGBoost regressor. You go here, click on accelerator, click on GPU, and turn on GPU. Okay, so now this is going to turn on GPU. Let me fix it. Okay, let's try again. And GPU is turned on. And now one thing that we would do is we will add 3 new arguments to XGB regressor. So let's minimize this, remove njobs, and instead of njobs you have tree method, which is GPU underscore hist, GPU ID, that is 0. We have only one GPU, and ID is 0, start from 0. And predictor is GPU predictor. If you do that, your model fit and model predict is going to be really super fast. Remember to turn GPU on. If your GPU is on, you will see something like this. You will see GPU here. Okay, so now, okay, let's import and let's run this part, and it's going to be really very fast. You will see that. Let's run this part. Yeah, one more thing. Today we are doing feature engineering. So competition, sorry, 30 days. Part 2 is feature engineering. Okay, so let's see what fails. Okay, we don't have the folds data, so I can just copy this and I can go here, add data, and here I can search for dataset 30 days folds. So I have 30 days 10 folds. It's made by me. 30 days folds. It's also made by me. I will add 30 days folds, which is 5 folds. Okay, and I have added the data. Okay, and now I can try to read it again. See what happens. See if it runs or not. So here we have done nothing. It's just like last time. Okay, useful features is not defined. So we forgot to copy something, and okay, let's go up and let's copy this part. And let's just paste it here. Everything in one cell. So now it should be fine. Ordinal encoder is not defined, obviously, because now we import from sklearn, we import pre-processing. So we do pre-processing dot ordinal encoder, pre-processing dot ordinal encoder. Okay, so yeah, today we are doing feature engineering, and this is same as last time. We just have ordinal encoder for all the categorical variables, and we are calculating the CV's, the fold scores. So now see how fast it is. Now it took so much time last time, but now I don't even have to pause. So the first kind of feature engineering that you can do is, but wait for it. Let's look at the data. So if we look at the data, it's very difficult to do feature engineering without knowing what these variables mean. So if you don't know that, so you can do some plotting. Someone has posted a very nice exploratory data analysis kernel on the Kaggle forums on code in the code section. So you can take a look at that. I'm not going to do it, but the thing here is there is not much that you can do with features. So you don't know about the features, and if you know about the features, it's easy to do feature engineering. But when you don't know, you have to shoot in the dark. So you have to throw spaghetti at the wall and see what sticks. And if it sticks, it's good for you. So we have the data frame. All the features are anonymous, but we have two kinds of features. One is categorical, another one is numerical. So the first kind of feature engineering that we can do is with numerical variables. And what we can do with numerical variables is we can standardize them. What does standardization mean? So standardization means you subtract mean value from the feature and divide it by the standard deviation. So standardization. This is something that we can do. And to do that, we come here. So let's create a new list. So we have the object columns, and let's create a new list and call it numerical columns. Numerical calls. Call for call in useful features if cont in column. Okay, so if the feature, or you can just do if call dot starts with cont. So if call dot starts with cont. So this is also one way of doing it. And now here we will initialize our standard scalar. So I will just say scalar is pre-processing dot standard scalar. And this is also from scikit-learn. So scikit-learn pre-processing has all different kinds of pre-process functions that you can use very easily. Let me copy this part and paste it here. Now instead of numeric object column, we will be using numerical columns, and instead of ordinal encoder, we are using scalar. And you're done. So this is one of the things that you did is you have ordinal encoder, ordinal encoder for the object columns, and you have standard scaling for numerical columns. So you subtracted mean value from each column and divided by the standard deviation of that column. And that's what this function is doing. Now we run it again. and we see if we have any kind of improvement in scores. So previously here it gave us 0.725, which is our mean score, and my standard deviation in all these folds is 0.001. Okay, so it's 0.724 to 0.726. And now it seems to me like it's still 0.725, but it's a little bit better. So if you look at 0.7256, here we have 0.7256, but now we have 0.7255. One thing that you have to remember is you also need to play around with XGBoost parameters. So in this video, I'm going to show you the feature engineering, but I'm not going to show you how to play around with the parameters of XGBoost, and that's something you have to do on your own. Maybe in future videos, I will show you how to do that. And whenever you change features, you have to change the parameters a bit. And otherwise it's going to be similar scores, or yeah. So right now we are just using default parameters. One more thing that you can do is probably fix the fold for each XGBoost regressor, but let's leave it like this. So standardization. So this is one of the things that you can do. Another thing that you can do is you can use normalization, and for that all you need to do is replace standard scalar by normalizer. So yeah, this is something else that you can do with numerical features. So you try it on your own and let me know if it performs good or bad. Another thing that you can do is, let's copy all these things here and let's remove the scalar part, and we come here, we have the numerical columns, and we can do log transformation. So there's a lot of different kinds of transformations that you can do. We will just try simple log transformation and see if anything happens. Maybe it won't help. So I will go through each and every column in numerical columns, and I will replace every numerical column by the log of 1 plus that value. So I will say df call is equal to df np.log 1p, which is doing log of 1 plus x, and here I can just do df call, and the same thing we have to do for df test. Now this thing we don't have to do like for training and test separately, it's just a transformation. So yeah, we just do it like this, and let's run it. Okay, now what are the scores? Maybe a little bit better, but I don't know, and I don't want to know. This is something that you should figure out on your own. Another thing that we can do is we can create polynomial features. So scikit-learn has a function for this called polynomial features. And I will just write sklearn, and we can take a look at the documentation and see what it does. So you can create polynomial features of different degrees. You can have only the interaction features if you want, and you can include a bias term, so that will be all ones. So if you have two features a and b, the polynomial features that will be created will be 1 a b a square a b b square. And similarly, like for degree 3, you have features up to 3 degrees. So doing this is very easy. You say polynomial features degree 2, and you fit on this data, and it gets transformed to something like this. If you create only the interaction only features, it will give you only AB. So and a square and b square. So yeah. You have the bias term, you have a, you have b, and AB. So no a square and b square. Sorry, I was not correct. And to do that, let's go to our notebook here and add polynomial features. So I'm just going to copy this one, or anyone, like I can copy this cell. Yeah, here we have scores 0.725 and 0.001. So you see how fast it is using the GPU. And here I can say polynomial features. The thing about polynomial features is when you fit them, it's going to create a numpy array. So now you have to convert that numpy array to pandas data frame 2. So I can initialize polynomial features as poly and call it preprocessing dot preprocessing dot polynomial features, and inside this I will write degree equal to 2, interaction only equal to true, because we don't need the features like a and b and a square and b square. We just need the interaction only features. And we got interaction only equal to true, and we also have include bias. We don't need to include the bias term, equal to false. So once we have that, we can now fit it on the numerical data. So I will just say train underscore poly. So this is a new numpy array, is poly dot fit underscore transform df, and here I can write numerical columns. So now you see I just fit transform on both train and test, and that's because it's just polynomial features. It's just multiplication of one column with another, so you don't need to care about anything else. So I got train poly, I got test poly, and now I will convert it to a data frame. So let's call it df underscore poly equal to pd dot data frame, and here I can write train underscore poly and comma columns. So I can name the columns. If I have to name the columns, let's name them with f string. And here I can write here I can write poly underscore the feature number, which is I, for I in range, train underscore poly dot shape, so the number of features that it created, and 1. And similarly you can do df underscore test poly. So here you have test and columns, and here you have test underscore poly. So the number of columns here, so poly underscore 0, poly underscore 1 till the number of columns in train underscore poly. So you have converted them. Now let's update these things again. So I'm doing it in a very old copy paste way, copy pasting code, not very good. But now I have to update my useful features. I have to update my object columns, and I don't need numerical columns. It's not even being used, numerical columns. Let's search for that in the last one. So we are not using numerical columns anywhere here. So we are using all the columns anyways. So and the ordinal encoder. So everything is the same. All that you have done is used polynomial features of degree 2. Let's see if it improves our scores. So maybe we have a small improvement, maybe we don't, who knows? You have to compare. We can also do degree 3, so it's going to create a lot more features. And the more features that you add, more time it's going to take. But if you use GPU, it's probably going to be fast. And with features, you must update the hyperparameter. But because if you're not doing that, I don't think it's of much use adding features. Okay, so now one more type of feature for numerical columns is to bin them. So this is something I'm not going to do. I'm going to leave it as an exercise, binning the numerical features. So keep the original numerical features. Let's not write that. Keep the original numerical features and also create bins of all those numerical features. So as we did when we were doing like when in one of the exercises we used pd.cut to create bins. So that's what you will be using. Okay, so divide them into bins and add them as new features, and these will become categorical features. And this is something you have to do on your own. Okay, the next one is one hot encoding. So let's go back to the original one and take all these, and instead of ordinal encoder, I can have one hot encoder. And in one hot encoder, we have studied that we need to do sparse equal to false if we want the dense matrix. And that's what we are doing here. And handle unknown, we add ignore. Okay, so if we add ignore, it's going to handle the unknown values in the test set. There will probably be some unknown values in test set. Now, one hot encoder creates numerical columns. Sorry, it creates an numpy array. So that's why we changed this to train OHE, xvalid OHE, and xtest OHE. Now we have, okay, let's fix the naming too. Not that it matters, but yeah, we should use proper naming. And now we need to convert this to, again, data frame. So we will use the same technique as we used before. So let's copy this part. So yeah, we are using so much code, right? Reusing so much code. Train OHE, and this will be, I can call it OHE underscore I and xtrain OHE dot shape. So I got this here, and same for validation and test. Xvalid, xtest, and now you just need to concat it with the data frame that you had. Did we concat here? df poly is train poly, test poly. Okay, we did not, and that's not good. So maybe our score will change. So here we also need to concat it. So df equal to pd dot concat it with df comma df underscore poly comma axis equal to 1. So you're adding new columns to the data set, and it's a big mistake if you didn't do that. You created a feature, but you ended up not using them. Okay, till we calculate the score again, we come here, and then we create xtrain again, and using pd.concat. Here we have xtrain comma xtrain underscore OHE, and same axis equal to 1. And then we have x underscore valid, and this will be the same valid, and you have the same for test. So now you are using the one hot encoded features instead of the ordinal encoding. Okay, let's see, input contains none. So now we got some problems. Ordinal encoder dot transform object columns. Okay, let's see what's going on. What's going on is we did a mistake, df underscore test underscore poly, and then it should be fine. Okay, moving back. So this is your one hot encoder, and now you have used one hot encoder for your categorical columns. Numerical columns stay the same, and now we move to the next feature. The next feature can be a simple, it's again exercise. So one hot encoding of categorical variables plus standardization of OHE and numerical. So when you did one hot encoding, you converted your categorical variables to zeros and ones, lots of zeros and ones. Now you combine them with numerical data and standardize both of them together and see if it improves your score. So this is one more way. So here I see no improvements by adding the polynomial features. Okay, so these features may improve your score, they may not improve your score. It also depends on how much hyperparameter optimization you do, and that will also be a new part. Okay, so that finishes 30 days part 2 feature engineering. I hope you liked the video. If you did, click on the like button, click on subscribe, tell your friends about it, that is, share the video. And see you in the next part. Good luck with the competition.